Hi, welcome to grade 12 university level chemistry. This is the video for 7.6, the solubility product constant. So far you've learned about balancing chemical equations and trying to calculate chemical equilibrium. Now we get into solubility equilibria. This involves dissolving a solid into a solution. So for example, we see silver nitrate and hydrochloric acid, and it creates silver chloride. Well, if you were to take a look at the net ionic equations, you would cross out or remove the nitrate and the hydrogen, and what that would do is leave you with a net ionic equation of just the ions involved in forming the solid precipitate. We can turn this into a equilibrium question by reversing this. So we put the silver chloride solid on the left-hand side and the ions on the right-hand side of the equation. At this point, we will define a new K value. This is called the solubility product constant. And also remember that when we make a KSP equation, that the coefficients in front of the ions will become the exponents. So for example, in iron 3 hydroxide, we see that the iron has a coefficient of 1 and the hydroxide has a coefficient of 3. This translates into the KSP expression whereby the OH has an exponent of 3. For silver sulfide, we see a coefficient of 2 in front of silver ion and a coefficient of 1 in front of the sulfide ion. So in the KSP expression, there's an exponent of 2 for the silver ion. And here's a third example. We see that there's a 3 in front of the Ca and a 2 in front of the phosphate. Therefore, the expression for the solubility product constant will have an exponent of 3 for the calcium ion and an exponent of 2 for the phosphate ion. So let's get some definitions out of the way here. The solubility product constant expression can also be called the solubility product constant equation, or KSP equation. So the KSP can be calculated from this equation. That's the first purpose of this equation. The second purpose is to find the molar solubility. That is to say, how much will a solid dissolve into water in terms of moles per liter. The KSP expression can also be used to tell if mixing two solutions will create a precipitate. Finally, we can use the KSP equation to determine the effect of having a common ion effect. We'll discuss that later. The first one is to calculate the solubility product constant. And here we see an example. A scientist prepares a saturated solution of lead 2 iodide. Now remember, a saturated solution means that the solution can no longer dissolve any more of that solid. That means that there's still some solid left over on the bottom of the beaker. If you were to take an independent measurement of the concentration of one of those ions, let's choose the lead 2 ion, the scientists found that there was a concentration of 1.3 times 10 to the power of negative 3 moles per liter. So our task is to calculate the KSP. First, and always first, is to write the balanced chemical equation. And we're going to write this again backwards. So the lead 2 iodide will be solid on the left-hand side, and it's going to dissolve into water and form two ions, lead 2 plus ion and iodide ion. Because this is a dissociation reaction, we look to see what we need to do to balance this out. So there's a 2 after the I here, and we're going to put that in front of this ion on the right-hand side to make sure that it's balanced. The coefficient for Pb is 1. Then we make an ice table. So the ice table will look like this. You write the balanced chemical equation on the top, and you have the initial concentration in your first row. Since lead 2 iodide is a solid, we do not write any numbers in here because, again, we do not write concentrations for solids. On the right-hand side, you see the lead ion. The lead 2 ion has an initial concentration of 0 because initially it was just clear water. That was before you put any solid into the water. Then we also see the same thing happens for the iodide ion. The initial concentration is 0 for both. Then what's the change? After we drop the solid into the water, the concentration changes. So the lead ion increases by a plus 1x. The iodide ion increases by a 2x. So we know that the water will now contain more lead ion and more iodide ion than initially. Finally, once it reaches equilibrium, and we have an equilibrium between the ions and the solid, we'll see that the final concentration for lead ion will be X, and the concentration for iodide ion will be 2X. And there's nothing we can do about that for now. But when we use this number here, we can calculate the KSP. So the scientists measured the equilibrium concentration of lead to be 1.3 times 10 to the power of negative 3, which means that we just need to substitute the value of 1.3 times 10 to the negative 3 into our equation. So we can simplify this equation first, and we see that we have an exponent here. So 2x times 2x will be 4x squared. Then we multiply x with this 4x squared and we get 4x cubed. So now we substitute 1.3 times 10 to the power of negative 3 moles per liter into the value for x. So 1.3 times 10 to the power of negative 3 to the power of 3, do the exponents first, gives you this number here. Multiply that by 4, gives us our final answer of 8.8 times 10 to the power of negative 9. Remember, KSP values do not have units. So now we are going to go to the second function of using the KSP expression. How much solid will dissolve in water? So we're going to call that molar solubility. The KSP equation is useful for 25 degrees Celsius experiments. This is standard. So the way that we figure out the molar solubility is by creating an ice table like we just did, and by substituting our value of KSP into our KSP equation. It is important to note that what we're looking for is X. The value of X has the same value of the molar solubility of the solid that's being dissolved. The KSP for this example, we're doing a new example here, silver sulfide. The KSP is 1.6 times 10 to the negative 49. That's extremely small. So we're going to calculate the molar solubility in moles per liter. First, again, create a balanced chemical equation. There you go. Put it into an ice table. The I stands for initial concentration. So we're going to dissolve this solid ionic compound, the silver sulfide, into water, pure water. There's no ions in pure water, so the initial concentration of these ions in the product side of the equation is 0. Then looking at the coefficients, we see that the change in concentration will be 2x for the silver ion and 1x for the sulfide ion. At equilibrium, we'll see 2x and x respectively. Remember, pure solids and pure liquids do not have concentrations, so we don't put a number into the left-hand side of the equation here. So now that we have done that, we're going to make our KSP equation. It's also It's also called the solubility product constant equation. So the silver ion has a coefficient of 2 because there's a 2 there. We're going to put an exponent of 2 there. The sulfide ion will have no exponent. It'll have an exponent of 1. Then we'll substitute our values into the equation. We don't know the molar solubility. That's what we're looking for. So we're not going to substitute the number into the x. We know the KSP value, 1.6 times 10 to the negative 49. There are no units. From here, we're going to do some algebra and simplify this into 4x cubed. So if you were watching carefully, you'll notice that we put a 2x in the ice table for silver. That's why there's a 2x in here. We also see that there's an exponent of 2 on the silver ion in the KSP expression, right there. And people always say, okay, you're doubling it up, you're counting it twice, it's going to be wrong. No, this is not a mistake. This is important. The ice table shows you how this solid will dissolve into 2 different ions according to these ratios of a 2 to 1. It's a stoichiometric ratio. The KSP expression is completely different. The exponent here is based on the balanced chemical equation from before, but it's how the KSP value was determined. So you need to have this exponent there. Once again, after you substitute the value of KSP and you have simplified your algebraic expression to a 4x cubed, you can solve for x by dividing the KSP by this coefficient of 4. Then you take the cube root to give you 3.4 times 10 to the negative 17. This is the molar solubility of silver sulfide. 3.4 times 10 to the negative 17 moles per liter. There are units when you're calculating the molar solubility. There are no units for calculating the KSP. So note that difference. Okay, so this slide shows how there's seemingly no relationship whatsoever between the KSP and the solubility of different compounds. So here's a 10 to the power of negative 8. We look at the power of 10. And here's the solubility, 10 to the power of negative 4. Here's a 10 to the power of negative 9. And this solubility went to 7.2 times 10 to the negative 4. And here's 10 to the negative 12, a really low KSP. And the solubility is 6.9 times 10 to the negative 4. It's almost exactly the same as this barium iodate. So you can't just look at the KSP and say, oh, I know what the solubility is going to be. You have to do the calculations. The next function of the KSP expression is to determine whether or not a precipitate will form if you mix 2 solutions together. We did this in grade 11. You might have remembered it as the solubility lab, the precipitate lab. And what you would do is you mix 2 solutions together, and if you check the table and it said that it was mostly insoluble or slightly soluble, then you would write down, or you would assume, that a precipitate will form. Now, that was qualitative. Now we're going to get into the quantitative version of that, and that's by using something called the trial ion product, Q. And the trial ion product can be determined using this exact same formula for the KSP. If the trial ion product, if Q is less than KSP, then the equilibrium will shift to the right. If it shifts to the right, then a solid will not form. Next, if the Q is greater than KSP, then the equilibrium will shift to the left. Now remember, we put the solid on the left-hand side of our equation, and therefore, when it shifts to the left, a solid will form. And this slide shows exactly what I just said. Now, you might be asking, what happens if Q is equal to KSP? In that case, there is no precipitate forming because it hasn't shifted to the left. The only time where you have a precipitate form is if Q is greater than the KSP. Here's an example. We have two solutions, sodium carbonate and calcium nitrate. Will a precipitate form? They give you the volume and the concentration of each of the solutions. So, your first step is to write a balanced chemical equation of sodium carbonate and calcium nitrate. There you go. You'll use a double displacement reaction to form a precipitate here. Then, using this solid, you will write a balanced chemical equation showing the dissociation of calcium carbonate into its two ions, calcium and carbonate. From here, you will write the KSP equation. So this is exactly the same as what we've been doing earlier in this lesson. You will go to the table in the back of your textbook and you'll look up the KSP for calcium carbonate. It happens to be 8.7 times 10 to the power of negative 9. So this is where it gets tricky. Now remember, you are mixing two different solutions. So when you mix them, the concentrations will change. What we're particularly interested in is the ions, calcium and carbonate. What are the initial concentrations of these two ions after you mix them? So you would think that, okay, carbonate must be 0.050 molar and calcium must be 0.0020 molar. But remember, when you mix solutions, you increase the volume. So this is a question which is quite nice. You have the exact same volume of both solutions, which means that when you combine the two of them, the concentrations will just be halved. So the concentration of carbonate should be 0.025 molar, and the concentration of calcium ion should be 0.0010 molar. If you don't believe me, we can do the calculations. Remember C1V1 equals to C2V2, the dilution equation from grade 11? Well, that's what we're going to use here. The initial concentration for carbonate was 0.050 molar. Carbonate came from the solution sodium carbonate, and the initial concentration of that was 0.050 molar. When this dissociates, you create one carbonate for every sodium carbonate that you start off with. So that's why the concentration of carbonate is exactly the same as the concentration of sodium carbonate. So you put that into C1. The initial volume is 0.02500 liters. That's 25 milliliters in a liter. Now we have to do that because the units for concentration are moles per liter. The new concentration is going to be called C2, and the final volume is going to be the two solutions volumes mixed together, so 50 milliliters. Originally we had 25 milliliters and 25 milliliters. So now we have 50 milliliters, and when we do the calculations, we see that our concentration went from 0.050 mole per liter to half of that, 0.025 moles per liter. This is the concentration for CO3. The same thing happens with calcium. The initial concentration was 0.002 moles per liter and ends up being 0.001 moles per liter. It's important to note that the initial concentration for calcium is exactly the same as the concentration of calcium nitrate, because when calcium nitrate dissociates, you get exactly one ion of calcium for every ionic compound or formula unit of calcium nitrate. What do we do with these concentrations now? We put them into our equation to find the trial ion product. 0.00100 and 0.0250 are multiplied together to give us this number. So Q is bigger than the KSP. So if Q is bigger than the KSP, then the equilibrium will shift to the left. And if it shifts to the left, a precipitate will form. The next topic is the last topic, the common ion effect. This is when you try to dissolve a salt or an ionic compound into a solution that's not water. It's going to be a solution that already contains some other salt in it. So for example, You have a solution of salt water, sodium chloride, and you're going to try to dissolve some silver chloride into it. Because they both share the common ion of chloride in the solution, the silver chloride will have a much more difficult time dissolving than it normally would. Let's try this with an example. Barium sulfate. What is the solubility of barium sulfate in a solution of sodium sulfate? The concentration of sodium sulfate is 0.250 molar. You can look in the back of the textbook to find the KSP of barium sulfate. So, first, write the balanced chemical equation, and you see barium sulfate will dissociate into barium ions and sulfate ions in a 1-to-1 ratio. Make your ice table, and you can see that you don't have a zero under the sulfate. The sulfate ion has an initial concentration of 0.250. That's exactly the same as the concentration of sodium sulfate. So when sodium sulfate dissociates, it will create one sulfate ion per formula unit of sodium sulfate. Therefore, the concentration of sodium sulfate and sulfate ion will be identical. Here we have our ice table, and we have solid on the left-hand side and no numbers because a solid does not have concentration. Barium ion, 0. Sodium sulfate does not contain any barium ion. Sulfate ion, 0.250. Okay, so we went through that. The change in concentration, plus x, because there's a coefficient of 1 there, and plus x, because there's a coefficient of 1 there. That gives us an equilibrium concentration of x and 0.250 plus x. I don't know if you've seen this before, but when you have a 0.250 plus x, when you have a binomial here, that causes problems in your calculations later on. What we're going to do is we're going to write the KSP expression. KSP equals to the barium ion multiplied by the sulfate ion. We're going to substitute the values that we know, and that's the KSP value here. We don't know the x's. We got these two from the ice table. The bottom, this is called the equilibrium concentration. So use algebra to solve for x, and look what you get. You get a trinomial, second order. So how do you solve for x? You would have to use the quadratic formula. If you do the quadratic formula, you'll get two answers. One of them will be negative, and it's impossible to have a negative concentration, so we'll be using the positive concentration as our answer, and the answer is 3.5 times 10 to the power of negative 10 moles per liter. This is very time consuming, so we're going to use an alternative method called the hundreds rule. That's what you learned in 7.5. So let's review it again here. We start off with the assumption that x is so small that if you add 0.250 plus this really tiny number, you'll end up with 0.25. What this does is it allows us to simplify this part of the equation to this. The second line doesn't have a binomial here. That, as you remember, is the concentration at equilibrium of sulfate that we got in our ice table right there. When you divide it out, you get our answer of 3.5 times 10 to the negative 10. You can see that this is exactly the same as what you got if you were to have done the quadratic formula. So this saves a lot of time, but we have to actually do some checks to make sure that we can do this assumption that 0.25 plus x equals to 0.25. So what are the checks? There's an initial check and there's a final check. So the initial check you do before you actually start doing these calculations. And if either of these checks fail, you must solve the question using the quadratic formula. The first check is the hundreds rule check, and that's why it's called the hundreds rule. It's the initial concentration of your common ion divided by the KSP. If that quotient is greater than 100, then you can make this assumption of 0.25 plus x is pretty much 0.25. So let's use the numbers from this example, and we'll go right into it. It's 0.25 divided by 8.7 times 10 to the negative 11 giving us 2.9 times 10 to the power of 10. This is a humongous number. It's much greater than 100, therefore we can use the hundreds rule. And this was the assumption that 0.25 plus x turns into 0.25. So I just wanted to make a little comment here, and that is whenever the KSP is smaller than 10 to the power of negative 4, that's the magic number. If you have a KSP smaller than 10 to the power of negative 4, so 10 to the power of negative 5, 10 to the power of negative 6, this is way smaller than 10 to the power of negative 4, you're going to find that the hundreds rule will pass. You'll get a quotient that's greater than 100. Okay, so after you figure out your answer, you know what x is, you have to do another check. You have to make sure that this x is less than 5% of the initial concentration. So if this x is less than 5% of this 0.25, then the hundreds rule assumption is valid. Here's how you do it. X divided by initial concentration times 100% must be less than 5%. The final answer for x was 3.48 times 10 to the negative 10. The initial concentration of the sulfate ion was 0.250. You divide those two, multiply by 100, and you get 1.39 times 10 to the power of negative 7%. This is incredibly small. It's way less than 5%, so your assumption is valid. Again, if the 5% rule fails, you must use the quadratic formula to solve for x. That means you have to start all over again. Let's compare just how important the common ion effect is. So we just tried to dissolve barium sulfate into sodium sulfate, a solution of sodium sulfate, and the molar solubility was incredibly small, 3.5 times 10 to the negative 10. If we tried to dissolve barium sulfate into pure water, this is what our ice table would look like. After doing all the calculations, we see that the solubility of barium sulfate in water is 9.33 times 10 to the power of negative 6 moles per liter. That's 10,000 times more soluble than it is in sodium sulfate. So these calculations show that the common ion effect is very important and that it also is consistent with Le Chatelier's principle. Well, that's it for now. I know this is a really tough subject to learn, so you may want to go over parts of this video over again. Definitely recommend that you ask questions when you need to and do as many practice problems as you can. Take care.